Yeah, just for your information, I sent out an earlier e-class announcement this morning. I couldn't really make it to the in-person office hour today. So instead, there will be a Zoom session somehow on Sunday, right? If that hour work for you, you can feel free to the Zoom. You can check the detail on the e-class announcement. But I'm gonna also announce on Zoom office hour regularly pretty soon, okay? All right, nothing else special to announce. I think we're good. I think after today, we got one more week before the reading week. And after the reading week, you guys will get very busy with other assessment, like a test and also project. And ultimately, of course, after another 6 weeks will be the exam, right? That's kind of expected. So let's now do a quick recap about what we said on Tuesday. And then we'll move on. Okay. There we go. Okay, sorry about that. It should be here. Yeah, beg pardon. Just let me adjust that. I should have done that before the start, but now it's there. Okay, good. Okay, so from last time, let's see quickly. Right, so we went over in detail this algorithm about subset construction, especially how we convert from N of A given as an input into the D of A, which is going to be each state in the D of A will be a subset of the N of A states. We call the subset states. Right? We went over in detail about each different ingredients about the algorithm. Please go over that. And also you can use maybe either this example here or other example just to run the algorithm and know how to trace it. Specifically, you want to know about how these two variables, reachable and to discover, will actually change between the iterations. I think that's really gonna give you the good sense about how the algorithm works. If you got any trouble understanding it, let me know. And then we talk about why we should really got this extra set brackets over here, right? I think one of you guys actually asked during the class. It's a great question, so I clarified that. Just make sure you also get that point to really understand the algorithm. And then we talk about, in theory, if you want to convert from a particular N of A into a D of A, because we know that every state in the ultimate D of A is going to, every state there is a subset of the states in the input N of A. So in theory, you can get 2 to the power of how many states you have in the N of A. It can be exponential, if in theory. However, in practice, if you use a lazy evaluation method, it's not going to reach exponential. You might, but it's not very likely, depending on the specific input. Okay, but for example, the input that we use in the class example is way fewer, it's way smaller than exponential, right? But you just gotta know how to figure out exactly how many subsets there are, right, for a given particular N of A, right? It's just basic math. And again, the basic math is actually summarized in the review slides that's already on the lecture site, right? You may want to go over that as soon as you can, and let me know if you got any questions. All right, we'll talk about epsilon N of A. It definitely gives us the convenience of using the so-called epsilon transition, which can be very useful if either you want to have some kind of a concatenation of different independent patterns, or if you somehow want to kind of union 2 different independent patterns. It will be very useful to use concatenation. So you also see that when we actually try to do the regular expression into epsilon N of A, we also see something similar. When you got concatenation in regular expression versus when you got the plus operator for regular expression. So when you want to get ultimate epsilon N of A, it's actually very logical about how you can do divide and concur. Right? We'll talk about it as well last time. Okay? You can look at the example yourself. All right, and then we talk about this particular example here. So this is indeed an epsilon N of A. Number 1, you can see we got epsilon transitions right here and also right here, right? We got 2 instances of the epsilon transition. And also it's non-deterministic. You can see, for example, 0 here and 0 here can bring you to either Q1 or Q4, right? So definitely non-deterministic. And we also did some tracing about different inputs, right? This one, and this one should be rejected. You want to see exactly how, okay? And then we spoke about how you can extend the transition table for epsilon N of A. Basically, you just need to have one more column for the epsilon transition. And just be aware, the alphabet for the epsilon N of A does not include the epsilon. Epsilon is not a valid symbol to be included in any alphabet. So the way we do it is explicitly union the alphabet with the epsilon possibility, right? Just notice that. So this extra union here just corresponds to the extra column that we have, right? We also talk about how you can work out the corresponding ending set of states, right? By doing an epsilon transition. You can also take a look. And today we're going to somehow build on top of this. We'll get there. So that was kind of the last part about the epsilon N of A that we spoke about last time. And as I said, we just wanted to kind of finish the topic first about how you can go from regular expression into epsilon N of A because it's more relevant to your assignment number 1. But I'm going to continue from here pretty soon. Let me just continue with recap. Okay. So we also started talking about how you can go from regular expression into epsilon N of A. Right? So we talk about doing that recursively, right? Systematically. So really, in theory, you can definitely take all the 3 base cases and take all the 3 recursive cases and code it up, right, as a transformation function to take any arbitrary regular expression as input and generates the corresponding equivalent epsilon N of A. That's what you can do. So we'll talk about the 3 base cases, and also we talk about the 3 recursive cases. Yeah, please take a look and then make sure they make sense to you. And we started doing this exercise over here. I would suggest we also complete it today, just to clarify some confusion. Okay. So what we did was we did up to this part over here, right? We got 0 plus 1, which is right here, and then we got star, which is the orange part about the extension. That's what we did, right? So why don't we just continue? We don't have much left. Why don't we see how we can finish the regular expression transformation by concatenating with this pattern here and also this pattern here. Let's just do that, okay? Before that, any questions from last time? All good? Okay, so the plan would be I want to definitely finish most of the lexical analysis, including I want to at least start talking about how you can minimize the D of A. The number of states in the DFA. At least we can start a discussion and do at least one example. There will be some exercises you can try. We may go over them as well. We'll see how the time will permit. And then there'll be one last bit about how you can implement a scanner by putting everything together. That might be something I will talk about in the beginning of on Tuesday, and then we'll move on to the syntactic analysis, which will be a little bit more exciting and more interesting, but a little bit more challenging to understand. That'll be the plan. All right, let's talk about this example here, and then we'll finish that exercise. Okay, so this is what we have got so far. Let me just make it a little bit smaller, right? So we'll know how we can concatenate. Okay, I'll make it just smaller right here. Okay, so this is what we have got so far. Okay, so there's one pattern here. You might be thinking which should be the start states overall. We'll get there in just one moment. Okay, but just know that we actually got this expression here, followed by this, and then followed by that, okay? But let's see, how about the 1 here? Okay, for the 1 here, let me just draw another one. How about blue? Okay, what about the 1 here? Right, that one should be pretty straightforward. We know that to really do the 1, you basically got this state here, and this state here. And then, we only recognize 1, but nothing else. Just 1 here, right? And then, since we are concatenating this pattern here with this pattern over here, so there should be a seamless epsilon transition. Once you are able to recognize the first part of the pattern here with a cleaning star, and then you can go directly to recognize the second pattern. So what you will get is, you will just get an epsilon over here. All right. So think about what we got here is the second pattern here, right here. Okay. And let's see the third one, which will be 0 plus 1. For 0 plus 1, why don't we use here? Okay. Sorry. There we go. 0 plus 1 right here. All right. And let's see how we can do that. Basically 0 and 1 and put it in parallel, right? So what we do is we can now go for, first of all, we got 0. So one pattern there will recognize zeros only. 0, and then over here. Okay, let me just copy that one there. Okay, we got another one here that's going to recognize 1 only. 1 here. And then since we actually got plus right here, so that means we're actually going to have some start states just for this pattern here, which will be right here. And we have some end states right here. Okay, so we can either go for epsilon to go for the 0 pattern. If that matches, we can go to the accept states for that particular pattern. Okay, let me not put the accept state just yet. I'll explain that. And then from here, we're just going to go for epsilon to the alternative pattern right here. Or we can go to the accept states for that particular pattern. All right, so that one there is the 0 plus 1. And then let me just highlight it. So that one there is the 0 plus 1 right here. And because we're concatenating the blue pattern with a pink pattern, so we just got to need some seamless epsilon transition right there. All right? So far, so good. I think the only thing left is, right now, this particular epsilon NFA is not exactly valid. Number 1, we do not have a start states. Number 2, we don't have any accept states. That means nothing can be accepted. No, not really, right? Let's talk about start states. Since we got 1, 2, and 3 patterns concatenated together, I'm basically adapting the rules from some textbook, which you don't need to read. It's optional. But I would say we follow the following convention. When you got multiple patterns actually concatenated together, 1 followed by 2 followed by 3, you can take the start states for the leftmost pattern as the overall start states. Okay, I'll write it down. So that means we can simply treat this guy here as a start states overall. Okay, I'll write down this rule. The start states of the leftmost epsilon NFA pattern is the overall start states. And symmetrically, you can, what about the end states? You don't really need to say this one epsilon and the end state. We could have, but just for the translation, we don't need that. Okay? So what we can do is we can simply convert the the accept state for the rightmost pattern right here to convert that into some accept states overall. Okay, I'll write it down as well. Okay, for this one here, the accept states or states. Oh, it should be just one. I beg your pardon. Because if you look at the bullet point about the rule, we always have just one single accept states. The accept states of the rightmost epsilon NFA pattern is the overall accept states. Right, so here we're talking about leftmost and rightmost. Leftmost and rightmost. And also talk about start states and accept states. Right, so this will correspond to the solution that you see on the slides. Yeah?
When I was doing this for homework, I did that from the beginning, and I also didn't put epsilon transitions between the 3 sub.
You mean, oh, I see. Somehow it collapsed these two.
Yeah.
Yeah.
Would that be considered incorrect?
As far as the translation is concerned, yes, you'll be incorrect. So I would say now that we know, right? So the convention we're going to follow will be, you'll do individual pattern first, and then if you're going to concatenate them, you got to show some explicit epsilon. Okay. Yeah. So let's say if I ever put this either in the written test or in the exam, I'll be very explicit. I would say, by following the transformation rule that we covered in class, now do the translation. So you got to follow this exactly. Yeah. Okay. How about we handle this after class? Okay, sure. Thank you. All right. Guys, are we okay with this? Good? Okay. Okay, so that one's done. And then let me just now go back to where we were about epsilon NFA. Just some formulation and some stuff we got to talk about first. Okay, some important one. And then we'll move on to minimizing DFA. Okay. Okay, let's see. Hopefully within 20 minutes we can be done with this part about epsilon NFA. Okay. And the slides I'm gonna go would be slide number 45. Okay. So we want to continue with the epsilon NFA. And just remind you very quickly, so last time we were talking about this particular transition table right here. Okay, right here. So as far as formulating a single epsilon NFA is concerned, we are basically done. So we know that it's going to be Q, sigma, delta, Q0, and F. That one is okay. So now we are basically talking about if you want to transform or convert given some epsilon NFA, how can you convert it into DFA? What we did last time was how to convert from NFA into DFA. But now we're just extending the input there. Okay, so let me just show to you. Give me one moment. So what we did last time, okay, was about how given some NFA, how we can convert that into DFA. Right? That's what we did so far. And now we are saying that if we extend the NFA notation with the so-called epsilon transition, so that'll be epsilon NFA. And now, given this epsilon NFA as input, how can we convert that into DFA? That's what we're talking about. And in order to do this, one critical step is to consider something called epsilon closure. Okay, I'll talk about it precisely in just one moment. But a very critical step about doing this conversion here, the conversion is still going to follow that lazy evaluation mechanism that we spoke about earlier, which I don't need to really repeat. I'll just highlight some important step when we actually see the actual lazy evaluation table. And you guys can actually do the exercise maybe after the class. So we don't need to spend too much time on that. But the critical extension we have to talk about is something called epsilon closure. So the idea would be, given any states, for example, over here, because from this particular state, without reading any further input, you might actually go to maybe another, S prime. You might go to another S prime prime, for example, right? As many as possible, as necessary, right? So in this simple example here, we would say that the epsilon closure of the state S is about the state itself plus all the other reachable states by following epsilon to there. Let me give you another example. This concept about epsilon closure is going to be recursive because let's say for S prime here, you might also have some epsilon transition, in which case you might get S prime prime prime. All right, this is also possible. So now, what will be the epsilon closure for S? It will be S itself. You might reach to these two states. From here, you might also reach there. So S prime 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 is also reachable from S by reading nothing. So all these will be considered as the epsilon closure for S. But we're going to see exactly how to calculate this algorithmically. Okay, I'll get there. So think about all these are so-called epsilon closure. Okay, all these are so-called so it's going to be called E-close, epsilon closure of S, starting from here, is going to be S itself and S prime, and also S prime prime prime. That's kind of the simplest case, but we're going to see how we can calculate this recursively, right? Which is not difficult to define, but I'm going to show to you. Okay? So once we talk about this critical step, we will be able to revisit the lazy evaluation method. Okay, let's talk about epsilon closure. All right, so we're given some epsilon NFA, and then we define epsilon closure. We call it E-close. Okay, so given a single state, Let me show to you. So let's say if I got E close, apply that to a single state Q, where Q is a member of the set of states. And then we're just going to get a set of states, meaning that the type of that is going to be a subset of all the states. Right? You can see the subset. That means epsilon closure is just going to be a set. Okay? More precisely, it cannot be empty. You should include just this, at least this, the state itself. Okay? So this is some property you can first of all note down, right? Right here. Okay? And then let's see the definition. It goes like this. If I want to calculate the epsilon closure of Q, first of all, I'm going to include Q itself. And then I'm going to go for the immediate reachable states from Q using epsilon transition. And then call each such state will be P. Okay? So this part over here means we are going to go over each immediately reachable states from Q via epsilon transition. So it's more like a loop. We're going to go over every reachable state using epsilon transition, and then we're going to union all their epsilon closure together. So this is a recursive part. Okay? For each such P, we're going to get its epsilon closure, and until we don't have any further reachable state using epsilon transition. Okay, so think about going for this. It's a recursive definition. And then also notice that the P over here is really every P that's immediately reachable from Q using the epsilon transition. All right, let's now do one example together. Okay. For example, let's see the epsilon closure for Q0. If I want to calculate the epsilon closure for Q0, all right, so Q0 is right here. By definition, it's going to be Q0 itself. And then I'm going to find out all such P. What's P? It's going to be all the immediately reachable states by using epsilon. It would be this one here, and also this one here, Q1 and Q2, right? Okay? So I'm just going to reach out to Q1 and Q2. Q1 and also Q2, okay? It's going to be union with the epsilon closure of Q1, also union with the epsilon closure of Q2. Again, the reason that we need to get Q1 and Q2 is because they are immediately reachable from Q0 using epsilon transition. Right? And then, of course, this part here is already done. Right? We'll just leave it over there. What will be the epsilon closure for Q1? Right? Let's say we get this part here. What about the epsilon closure for Q1? Okay, let me just put it aside right here. It's going to be basically Q1 itself. Is there any immediately reachable state from Q1 using epsilon transition? Q3, thank you. Thank you so much. Indeed. Absolutely. Okay, that's what we got to choose. So that one there is going to be basically union. The epsilon closure of Q3. You might be thinking, should we include Q5 at this point since there's also another epsilon? Not yet. We'll get there. Okay? Okay, that's the only one. All right? That's the only P that we have. And then we're going to look at another one. What about E epsilon closure of Q2? No? Epsilon closure of Q2. What would that be? What will be the set? If I ask you just in isolation, what will be the epsilon closure for Q2? Go ahead.
Q2?
Yes, I was worried that you might say empty set, right? It's not empty set, okay? Q2 itself, because there's no immediately available, there's no immediately reachable state using epsilon transition from Q2. So this one here would just be Q2 itself. And then no further recursion will be necessary, all right? So you can see so far we got Q0, we got Q1, we got Q2, all good. But we still need to figure out what's the epsilon closure for Q3 recursively, okay? Let's now do that. So for this one here, I'm just going to try to calculate further. And that one there is going to be Q3 itself. And you can see from Q3, the immediately reachable state using epsilon will be Q5. So union Q5. The epsilon closure of Q5. And then that one there, the E close of Q5, that one there you can see for Q5, we can't go any further. Agree? With epsilon transition, right? So that one there would just be Q5, right? Yeah, so now all we got to do is union all of them together. So we got basically this one here, this one here, this one here, this one here, and this one here. So what's the answer? So the answer is we got Q0, Q1, Q2, Q3, and then Q5. All right. Somehow only Q4 is not included. Okay, somehow. Of course, Q4 is not included and Q6 is not included, of course. Yeah. This is a very critical step to actually get done. And guys, make sure you know how to calculate epsilon closure, because it turns out when you want to do the lazy evaluation, for every cell, you will need to calculate epsilon closure. Okay, I'll show you exactly why. Okay? So the idea would be every time when you are trying to calculate what's the corresponding subset states in the ultimate DFA, when you try to do the lazy evaluation, you want to make sure the states you include over here cannot lead you to another state using epsilon transition that's not already included in the subset. Okay, I'll show you exactly what I meant. Okay? But that's how you can do the critical step, epsilon closure. Okay, good. Okay, let's now talk about some formulation first, and then we'll see some example, right? We got, let me see, 1, 2, 3, 4. Okay, good. Let's now go with that. Okay, let's go with this one first. A little bit of formulation. So when we talk about the transition function, right? For what we spoke about last time, by adding the extra column, that's only for the non-recursive delta function for epsilon NFA. And we got delta hat, it will be the extended version, the recursive version, right? So we talk about recursive version for delta for DFA, NFA, and also epsilon NFA. Right, we'll talk about all these. They're defined in a very similar way, but you guys' job is to really compare the formal definition and see the difference. Okay? But let's go over some quick definition here. For the base case, if I'm now currently in Q, I'm reading epsilon, right? Just don't forget, we are saying that the extended version, we are reading some string as opposed to a single character, right? So a sigma star. Okay? Let's now recall very quickly. In the case of the DFA, we simply say that one there is equal to just Q, no set. In the case of NFA, it's going to be the singleton set Q. But now, in the case of the epsilon NFA, You want to take a guess what it is going to be? Should be along a similar line of Q.
A set of states.
I agree, a set of states. What exactly will be the set?
That would be reached by epsilon transition from Q.
Which will be?
The E-closure?
The E-closure of Q.
Q.
Yeah, you're basically saying that right. I just want that epsilon closure, from you. Okay, exactly right. All right. So it's going to be here, epsilon closure. Just the E close of Q. All right. And for the recursive case, again, we got prefix, we got last character, right? If you remember, we got the prefix X, we got the last character A. Okay? Let me just draw you a diagram, and I'll write it out. It's very similar to how you do for NFA. Let's say we are now in Q, somehow. Okay? If we are now in Q, and then we are basically reading some prefix X, which is a string. And somehow we can get to a set of states. That's a Q prime is one of them. And then we're going to read the last character, A. And then we are ending with some Q prime prime is one of the. Think about this is how we start with. And then after reading the prefix, we're going to be in set of states. And Q prime is one of them. After that, we're going to end up with, after reading the last character, we're also going to end up in a set of states. And Q prime prime is also one of them. And one extra step is, for each Q prime prime, it might be reachable, there might be some other state reachable using epsilon transition. That's why we had to add one more thing. If you only consider these things over here, that's exactly how you define the delta recursive case for NFA. You can double check. So what we need now for epsilon NFA is to say from here, we have to read epsilon. And the way to calculate that would be E close of Q prime prime. So this is the extra step that we will need, okay, conceptually. And let's see how we can write it out. Overall, it's going to be a generalized union operator. And then we're going to get a set of states, okay? And then we're going to put something here, just in a moment. And here we're going to follow exactly how the diagram lays out. Okay? So first of all, we're going to do the delta hat. And then we go from Q, which is how we start with. And then you read the prefix. This one here is going to give you a set of states. And we say that Q prime is one of them. Right? That's exactly a Q prime that we have. And then we say that from Q prime over here, we're going to read the last character and get to Q prime prime. Okay? And we say Q prime prime is basically a member of, if you use a regular delta, which will read a single character. And that one there is going to go from Q prime, which is right here, and then the last character A. However, we cannot just say Q prime prime right here. We cannot do that. We need to find its epsilon closure, right? Right here. So what we do finally is to say the E close of Q prime prime. All right, so I try to present in a way that hopefully that can follow through the diagram for you to see the flow. So idea would be we read the prefix X, read the last character A, and then we calculate the E closure. All right, that's how things go. And again, when you guys study for this particular part of the formulation, I would suggest try to compare the recursive definition for delta hat from DFA, NFA, and epsilon NFA. So that'll be the best way to really see how things should be defined a little bit differently, right? Depending on the formulation, depending on the kind of machine you're talking about. All right, finally for the language, right here. It's going to be the language for epsilon NFA is going to be all the W, all the string, and it should be a member of sigma star. That one is pretty straightforward. And then This one here would be it would be identical to how we did it for N of A. We just want to make sure one state there is accept. So I'm going to say delta hat from Q0 and then read the entire input stream. The ending state after calculating epsilon closure is going to be a set of states. As long as one of them is accepting, then overall it should be accepting. Right? So it's the same condition as before. Intersecting with F is not equal to this one here. Right? So for this condition over here, it's just identical to how you did it for N of A. This condition is identical to N of A. Of course, the way you define the delta hat is a bit different, which is here. Okay? All right, any questions? Yeah, if you somehow get some like a 60%, 70% understanding, that's great. You just need a little bit more time to catch up, maybe to think a little bit more after the class. Okay? Let's now do one tracing together, right? I got basically two more for the epsilon N of A, okay? And then we'll take a short break. Okay, so let's now move on to the next one here. Okay, how do you actually process string using an epsilon N of A formally? Let's say we still have this particular epsilon N of A, right? So that's going to read the fractional number with the decimal digits in the middle. And let's say we want to process 5.6. Okay? I'm going to do just one or two steps together with you, but for the rest, you can try. Okay? You can also see the solution on the slides. 5.6. Let's start from the beginning. Q0 over here, we know that if you simply follow the epsilon transition, it's going to be, beg your pardon. So this one here, this will be the initial case. Initial state, which should be Q0. Okay. So this will be Q0. That will be the start states, which will be Q0. And the way to calculate it would be you want to calculate the E closure of Q0. Of course, you can follow through the recursive procedure I showed to you, but what about in this case? What would be the epsilon closure for Q0?
Q0, Q1?
Yeah, I agree, because you can see epsilon here, and from here you don't have any more epsilon. Very good. Q0, Q1. Okay, that will be the beginning part, right? Basically, for the beginning part, you gotta not just to convert the Q0 into a singleton set, but also get to calculate epsilon closure, right here. Epsilon closure. All right, let me try to show to you how you can process one character. Okay. So the idea would be we try to separate between calculating epsilon closure and also reading the character. Let's put that into two separate steps. Let's try to process the character first. After the initial states, after calculating the epsilon closure, we got either Q0 or Q1, right? So either Q0 here or Q1 over here. For each one of them, we have to see how we can, what the final state, what the next state would be by reading 5. For Q0 here, we're just going to calculate what's the delta of Q0 reading 5. And union with, and then we got Q1. Delta of Q1, and then reading also 5. Right, so 5 is the string we are trying to read. Right, 5 here, and 5 here. All right, for that one, you can definitely calculate, right? So from Q0, if you read 5, you get stuck, nothing, right? So basically, that one will be just empty set. And then what about from Q1 reading 5? Q1 reading 5, you can be in either Q2, beg your pardon. Q1 reading 5, it can be either a self loop or you can go Q4, right? Q1 or Q4. Okay, it's going to be Q1 or Q4. Okay, let's now calculate it. It's going to be just Q1, Q4. However, we have to make sure the final result, this is more like an intermediate result without considering the epsilon closure. We want to make sure Q1 and Q4, if there's any reachable states by epsilon transition, we should include them as well. Okay? So what we should do is Q1 and Q4. So think about Q1 and Q4. So let me just say Q1 here, pink, and also Q4 over here. We're going to calculate, finally, the epsilon closure of Q1. Union with the epsilon closure of Q4. All right? And that one there, let's do that very quickly. What's the epsilon closure for Q1? Q1, there's no epsilon transition. Thank you. And then, finally, bother you once more. What's the epsilon closure for Q4? Q4, agree? No epsilon transition, right? All right, Q4 right here. So that means we actually get Q1 and Q4. Of course, you might be saying, well, what's the point? This one here and this one here happen to be the same. It's simply because the epsilon closure gives you the same states, but not necessarily for every state you have to deal with. So that's why you got to keep moving. All right? All right, so this will be the final answer. And also, when you actually show your work in the actual exam or written test, well, if you're asked to already show your work, you got to make sure you actually calculate, number one, the regular delta, and then you got to show explicitly what's the epsilon closure. Okay? So from here, you're going to continue of reading dot and then reading 6. Okay? That would be your exercise. Okay, so for this part here, it will be exercise for you. Okay, give it a try. It's going to follow just like this step here. Okay, I'll leave the exercise to you. You can also see the solution on the slides. If you want some extra exercises, you can feel free to try these as well. Extra exercises. You can try, for example, 0.6. You can also try just dot. All right, give it a try. And just give you one more. Plus 23. Okay. Question?
Yeah, when we're reading the first 5, and we have 2 delta transitions and 2 epsilon closures,
Yeah.
can we union all 4 of those together? Or no?
That's not the way to go. Yeah, I see what you mean. Somehow this, okay, I see what you mean. The Q0, Q1 here comes from the Q0, Q1 here. And the Q1, Q4 over here comes from the result, Q1, Q4 over here. So you cannot simply just union, because what? The thing is, in order to know how many epsilon closure you have to calculate, it depends on the cardinality of this particular set over here. So let's say, just for illustration, if this one happened to be Q1, Q4, and possibly Q5, in that way, you have to also calculate the E-close of Q5 and then union them together, right? So you shouldn't really think about you're trying to union everything together. That's not the way to go. There's some dependency there about the order. You want to calculate first of the delta, which depends on the final set from the previous step. And then calculate epsilon closure, which depends on the union from the epsilon. So for the union of the delta result. Okay.
Sorry, one more question. Could you union the Q1, Q4 from the previous step with the E-closures Q1 and Q4?
Say it again, sorry.
So Q4 in the middle,
Over here?
above,
Above?
right above that.
Yep.
Can you union that with the E closures Q1 and E closure, epsilon closure Q4?
You mean union with this?
Basically, yeah.
You don't need to union with that because the calculation here is based on this. If you union them, you're just gonna get the same result.
Oh.
Yeah. So, Q1, Q4 is really the individual state that you have to calculate E closure. And we know that E closure will include these two states already. So there's no point to union this with this. This set here is guaranteed to be a subset of what you're going to calculate over here. The epsilon closure will only give you additional states if possible.
Okay.
This one here is more like a basis. Okay. But it's a good question. Yeah. All right. So guys, why don't we do one more, and then I got one more page about epsilon innovate, but we can do that after the break. Just one more. Okay. Okay, this one here it just kind of showed the show the lazy evaluation you have to do, right? So given this epsilon NFA, you're going to convert that into DFA, right? So I just want to do a single cell together with you, and then you can do the rest. Okay, let's see exactly how we can do it. Okay, you can imagine that the way we're going to start the lazy evaluation, we are still going to figure out what's this cell over here, and then we're going to calculate one by one. Okay, I already included the answer for all the rest over here, but let's see exactly how this one can be calculated and how this one can be calculated. Right? Just see these two. Okay, once we know about how to calculate these two, the rest will be calculating the same way. Okay. What about this one here? This will be the very beginning stage of your algorithm. So that one there really depends on the start states, which is Q0. Right? There should be no surprise to you. This part here would just be the epsilon closure of your start states, which would be Q0. And that one there we know pretty well is going to be Q0, Q1. Q0, Q1. Right? That's your starting point. You do not just put the singleton set of Q0. And you can think about this one here is the initial or start. State of the output DFA. And don't forget, we call this a subset states. And we got 1, 2, 3, 4, 5, and 6. 6 different subset states ultimately, instead of 2 to the power of 1, 2, 3, 4, 5, 6. Right? You can see it's way fewer than the theoretical maximum. All right, so that's about the first one. What about the second one? Okay, the second one there is going to go like this. This cell over here, and that one corresponds to some digits, right? The digit can be 0, can be 1, can be 2, can be 3, etc. Well, some digits. Why don't we just say 1 as an example? Or actually, you can just say D. It's a bit easier. So you don't need to have one column for 0, one column for 1, one column for 2. It's not necessary. Not necessary. Just say D, digits. All right, in order to calculate this one here, I will give you the steps right here. Okay. Let's say we are calculating digits. Very similar to how we did it right here. Very similar. Split them into 2 steps. Okay. Use a regular delta and then calculate E close for each of the resulting states. So what you will do is you're going to say, step number 1, you're going to do the delta of, it can be either from Q0 or it can be from Q1. Q0 and then take some digits. Union with the delta of the Q1 and take some digits. And this one here is going to give you a set. Pretty much like you have a set right here, Q1, Q4. And then for each member in the set, you're just going to calculate the epsilon closure and union them together. And you will get something like this, which might be larger. Okay, so step number 2. You're just going to calculate the epsilon closure So you're going to union epsilon closures of each member in the set S. For example, let's say if this is set S, right? Just from each member there, just calculate the epsilon closure, union them together. And you will get this answer over here, right? Exactly how we did it for this particular one. All right. You can just try that, and then you should really get an answer that's corresponding to what's on the slides. I'll suggest maybe give it a try, and then you will see the answer, right? And also, of course, calculating this from scratch is going to be kind of time-consuming, but if you really want to get thorough understanding and very proficiency from doing this manually, you may want to do as many cells as you possibly can. Ideally, if you can do it from scratch, that'd be great. But answer is all there. A final point to make before we take a break. So you want to take a look at accepting states. Because we know that in the source NFA is Q5. So any subset state that contains Q5 here, Q5 here. So these two are the accept states in the output DFA. Accept states of the DFA. Okay. All right, I got one more just about epsilon NFA, but we can take a short break and then we can get there. That one will be very quick, and then we can get on to minimizing DFA. Okay. Let me pause the recording. All right, so there's only one last page which will kind of formulate about what subset construction really is between when you actually want to convert from epsilon NFA into DFA. I think it might be a better idea to maybe, for those of you who actually do want to catch up with what we have been talking about so far today, you can do that, and then maybe I'll use this as an opportunity for us to recap on Tuesday. I can do that. That'll be a little bit better, because if I talk about it now, you really assume you are familiar with the subset construction process for epsilon NFA. Maybe you can do that on Tuesday. Okay. So that one there, so this is what we talked about before the break. And then the one which I'm going to revisit when we do the recap on Tuesday will be, let me tell you the slide number. Okay, this is something we talked about before the break. It will be slide number 50, right? Slide number 50 basically is just going to show to you if you want to convert from epsilon NFA into DFA using the subset construction and E-closure, what will be the correspondence, right? I'll suggest maybe review about the actual example, and then feel free to look at this slide here as well, and then we're going to use the actual page here to do the recap on Tuesday. I think that'll be better, right? So you can appreciate the formulation here a little bit more. Okay, that's what I would do. So for the rest of today, we got about 20 minutes. I think it would be a very good chunk of time to at least talk about minimizing DFA. That's pretty much the last stage for the lecture. Okay? Let's now talk about some general introduction, right? I'll revisit slide number 50 when we do the recap on Tuesday. And let's now talk about also a regular expression to epsilon NFA. We have talked about it last time. And then let me just show to you where we should start now. All right, here. Slide number 56. Okay. We want to minimize the DFA. And we actually got a regular expression. We can convert that into epsilon NFA, and from epsilon NFA, we can also convert that into DFA. That's what we have done so far. Okay. This is what we did last Thursday. And this part here is what we just did today, which is based on how we can do lazy evaluation from NFA into DFA, right? So these are something we have done. However, when you actually do the DFA that we got actually here is not guaranteed to be minimum in terms of its number of states. There might be some redundant states which we may want to get rid of, especially when memory size is actually a concern for you, okay, for your application. For example, it could be that maybe you're using your processor's maybe cache memory, in which case you really want to make sure that whatever program you're writing there should be as small as possible. So the fewer number of states in the DFA, the better. Okay, so we're going to see how we can do that. And the way you minimize the DFA is actually very interesting, right? We're going to study some algorithm, and then we're going to do some example, and we'll do some tracing together. Okay, we'll see how much we can do today. Okay, at least I can go over the algorithm with you and do 1 or 2 steps, and then you guys can do some exercises maybe over the weekend, and we can complete the exercise on Tuesday. Okay, I'll try to give you guys just enough so you can also do some independent work on before Tuesday's class. It's actually a very fun algorithm to study. Guys, I'm just curious, if you can recall distantly back in 2001, did you actually learn about how to minimize the DFA? You think so? Yes or no? Okay, maybe at least when I was taking 2001 as a student at York, I don't think I was taught that. But anyway, if you learn about it, great, but I can tell you that it's a very tricky algorithm, so you may have forgotten about the details already, but let's go over that. Okay. Slide number 57 is about the algorithm itself. Let's go over the algorithm very carefully, okay? And then we'll do some example. Okay. So the algorithm is about minimize the DFA states over here, and the input is some DFA, output is just another DFA, M and M prime. M here is a DFA. M prime is just another DFA. We will say such that the cardinality over here should be minimum. And also the behavior should be equivalent. We don't really prove about the correctness of the algorithm, we just assume it actually works. Okay? But hopefully you can get some fewer number of states in the output. Just before we dive into the details right here. Okay? So you might be wondering, there's 2 things we want to consider. Number 1, what if M prime is exactly equal to M? What does that suggest? Somehow you apply the algorithm to input M, but you got exactly the same DFA.
It was already minimum.
It's already minimum. That's exactly right, right? It's kind of easy to see. All right? That means the input is already optimized. That means no optimization was actually necessary. Was necessary. All right. Number 2, what if, let's say here, the number of states for M prime is actually strictly larger than the number of states in M. So M prime here is the output. Somehow the output number state in the output is actually strictly larger than the number of state in the input. Should that be expected? Not really, right? Because you're supposed to minimize. I can tell you that given that the algorithm is correct, this one should not be possible. Okay, just something you want to bear in mind as well. Should not be possible. Given that the algorithm is correct. All right? Just 2 side notes. Let's now go over these 2. This algorithm very quickly. I'll make some annotation, and then we can do some quick annotation about the algorithm, and then we'll see if we can do any example. Okay. So there are 2 critical variables, P and also T. Okay. Let's now see first of all where they are used. So P over here is actually used right here, and also right here, and also I think that's it. Okay, that's a P. And also for T, it's actually used right here, and also right here, and also we gotta update the T for every iteration. It's an iterative algorithm. Somehow it accumulates between the iteration, right? Okay, and then also you can see that T is over here, and also P is over here, right? I'm just trying to highlight exactly how these two variables are being used. Okay, but I will talk about exactly what they are. Okay, so P here is about somehow we try to partition the given the input DFA states into different partitions. And we try to keep doing the partition until we cannot do the partition any further. Then we know that the final states for the partition should be the optimized. Okay, so we just got P here. That'll be the refined partition so far, right? You can see some comments over here. Initially, just empty. And then this T over here is about the last refined partition. We'll see exactly how these two will change. Okay, but that one there you can see that's interesting. We are trying to do some initial partition here. It will be accept states and also non-accept states. So F over here is corresponding to the F over here, right? Accept states. And also you got Q set difference F, right? If you see Q here, Q will be all the states. For all the states, if you subtract all the accept states, there'll be non-accept states. So initially, we're just going to partition all the states into accept versus non-accept. That's what we'll do, first of all. Okay? And then we're also going to run a loop, which is going to be here. We say that we are going to keep updating the partition as long as these two variables are not the same. Okay? That means as soon as these two are the same, we should really stop and terminate. Okay? Let's write down that inside first. So this one tells us that as soon as P equals T, that would mean no further optimization can be done. No further optimization can be done. Okay, just no further. Okay. And then we are going to see that there will be a nested loop, basically, right? Because the P here is going to be a set of states. For each member in P, somehow we're going to choose a state from there and then do something here. There will be some iteration to be done, right? And then there will be some definition here called splittable. Okay, that's also something we got to talk about. Okay. Now, how do we understand this helper function? Okay, helper function over here. And then that simply corresponds to right here. Okay, splittable. Okay, right here. Yeah, just before we do anything, let me just explain that what that really means conceptually. So here, so basically given a partition, P, given a set of states, as a partition, a set S, actually. You know what? Let me just write it properly. Given a set S of states as a partition. Oh, beg your pardon, should be P here. Okay, there we go. P over here. Can we find A? So now notice that we talk about this symbol here. This symbol is very important, as we'll see that next time. So this, as opposed to subset, is a proper subset. That means we should find exactly the just a proper subset. Can we find a proper subset of P that can be split from the rest of P? Intuitively, that's what it means. I'll get to these two conditions a little bit later once we do the example. Okay? I would suggest I'll just do a little bit of setup for the example there, and then we can continue on Tuesday. Let's just use a few minutes. So this will be the example that I want to do to begin with. Okay, this one here. Let's say we're given this DFA. Somehow this DFA here, the number of states there is not minimized. But what this DFA is supposed to do, it wants to recognize either FEE or FIE, either one, right? Only these two strings should be accepted. That's what it wants to do. Currently, we got 1, 2, 3, 4, 5, 6 states, but it's not minimized. Somehow we want to see how we can do to actually minimize it. So why don't we just start with just a few steps over here, just to show to you very quickly. Okay, so let's say we start with this. Okay, I'll do some preparation job. Now, to start with, I want to show you the correspondence to the algorithm. If you see the algorithm over here, you can see the initial partition that we want to do is we're going to partition into the accept states and also the non-accept states, right? These two. Let's do that two partition first. That's what you should start with. So the accept states will be exactly this one here. And also this one here. The non-accept state is everything else. This one here, this one here, this one here, and also this one here. So initially we only got two partitions, okay? So you can think about only two partitions. And the variable you should really keep track of will be just P. Okay, I'll write it down first. So the initial partition will just be S0, S1, S2, S4, and then also we got S3 and also S5. Okay? And there's one more convention I want to talk about, right? So we don't need to do that anymore on Tuesday. You might be wondering, this cannot be a DFA because what about A, for example, right? If I read A, it seems like I will get stuck. There's no transition for A, right? This example was taken from some textbook, and there is an implicit assumption, which goes like, I'll show to you. Let me just go over that implicit assumption here so it'll be clear to you. So this one here is really equivalent to, we assume that there would be error states, like a dead states, SE. Right, SE over here, error. Error states. And then you can say the alphabets is simply just A, B, all the way to Z. Okay, so that's the alphabet. So let's say here for S0, only F is going to lead you to S1. What about all the other characters? You can think about for S0 here, everything other than F will lead you to the death states, right? Similarly, here from S1 over here, anything other than E and I is also going to lead you to the error states. So sigma set difference and also E and I, etc. Right? You can also do something very similar for here, right? So there will be some alphabet which will lead to the error states, and also something will also lead to the error states. Okay? Of course, if you read any further character, you also go to error states. If you read any further character, you also lead to the error states, right? But to really make the diagram a little bit cleaner, we don't really mention those transitions. Okay? And of course, once you get to error states, it doesn't matter what you're going to read further, it's just going to be sigma. Any character from sigma that will lead you to the error states. Okay? So for our example, I'm just going to put the error state still there, but I just wouldn't draw all those transitions. It would just make things unnecessarily complicated. All right, so what I will do is I'm just going to add the error state right here, SE. Okay, and then because SE should not be accepting, so that should be part of the pink partition. Okay, so let me just add it right here. Okay, it will be SE right here. So in the beginning, we got partition 1, and also we got partition 2. Okay. And this step here just corresponds to basically this part here. That's how we initialize it, and then we have to do these two initial assignments. Okay? So I would say before Tuesday, you don't need to continue with the exercise. Just get yourself familiar with how we initialize the P and T, and also in the very first iteration, somehow we have to let P be in T, and also T should be reset to be empty set. We're going to do this kind of reset for every iteration. That's something we're going to trace as well on Tuesday. Okay? Yeah, so on Tuesday, my plan will be I will finish off this minimization algorithm, and then there'll be a final snippet of code to show to you about scanner. And then we can move on to syntactic analyzer. All right, thank you. I'll see you next Tuesday.